Okay, in the last video, we just did a simple substitution, and we substituted in this equation for the force of gravity into this equation for acceleration. So we just plugged it right in. When you plug them in, you get this equation. And the nice thing that we saw was that the mass 1 on the bottom of the acceleration equation canceled out with the mass 1 on top of the force of gravity equation. And they canceled each other out, and they left us with the just big G times m2 over r squared. And that gives us the acceleration due to gravity. And on Earth, that happens to be 9.81 meters per second squared. Using mass as the mass of Earth, 5.97 times 10 to the 24 kilograms. And using as the distance, the radius of the Earth, the distance from the center to the surface, as 6.378 times 10 to the 6 meters. And just by using these numbers, and of course G, we'll always get something that's about 9.81 meters per second squared. And these things don't care, right? There's nothing in the equation for that other mass, right? So this is for all masses that are on the surface of the Earth. There's going to be acceleration due to gravity of about 9.81 meters per second squared. And I'm just going to show you another way that you can get to that conclusion. So again, if we write the force of gravity is big G times m1 times m2 over r squared. And I can rewrite this, right? I can just rearrange it and say, how about I write it as mass 1 times gm2 over r squared, right? Same exact thing. I just kind of switched the orders there. I'm allowed to do that because they were multiplying. And I also say, well, remember that force equals mass times acceleration. Well, I got a mass for you right here, right? And if this is mass 1, then this must be acceleration. They have to be, right? So, and that gave us exactly what we got before, which was basically that the acceleration due to gravity, right, this is all for gravity here, is big G times m2 over r squared. And that's just another way of seeing it, and also a way of showing you that it doesn't really matter what the mass of the other object is as long as it's on the surface of the Earth. Anything that we plug in here is definitely going to give us a different force, but it gets a different force because we're changing the mass but multiplying it by the same acceleration due to gravity. So let's just do another calculation, and let's find the acceleration due to gravity on the moon. So the moon has a radius of 1.74 times 10 to the 6 meters, and the mass of the moon is 7.36 times 10 to the 22 kilograms. So if we just plug these numbers in, so acceleration due to gravity is big G m2 r squared, we get, here comes another space thing. Alright, we get 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times 7.36 times 10 to the 22 kilograms, all divided by 1.74 times 10 to the 6 meters squared. And that will give you 1.62 meters per second squared. So that's the acceleration due to gravity on the moon, which is smaller than on Earth.